Welcome back to our series on applied regression analysis. I'm Mark Ledbetter. This is lecture video 50. We are in chapter 16, part 4. We're going to finish up chapter 16 in this video. Previously in this chapter, we are discussing how to select the best regression equation. And we gave the steps for selecting the best model. So far, we've talked about specifying the maximum model, specifying criteria for selecting model. I must tell you that in this textbook, they call it the F statistic, which is the p-value. That is the most common method. And then they talk about many others that are not commonly used, at least within the fields of application that I have worked with. The fields of application that I've worked with include safety, so engineering, operations type of thing, and medical, the medical field. And in both of those, we like to use the AUC, area under the curve, unless we're doing survival type of statistics. And then we talk about something that's very equivalent, and that's called the concordance. So the concordance for survival models, which is a whole nother area of statistics, and there are courses specifically on that. So we talked about the criteria for selecting models, and then we're talking about the strategy for selecting variables, and we talked about the all possible regressions, and the book recommends this method, but it's not always practical, and it's quite tedious to work through. We have done backwards elimination, forward selection, and stepwise selection. And in the last video, we were doing an example. So we were actually talking about conducting the analysis and evaluating reliability with split samples. So we will continue with that. In fact, we're going to finish up very quickly the example that we were doing last time. We had split the data into two data sets. So I will go back to this very quickly. We had this actual analysis where we were using weight, height, age, and sex. So weight is our response variable, and our maximum model we chose with these particular variables. So we had age squared, age cubed, height squared, height cubed, and sex, or gender. And so we were looking at using the CP and R, okay? And so we looked at backwards elimination, and we wanted to evaluate the reliability of the model as well. So we split it into two data sets, and so far we've only talked about the first data set, or data set 1. They did descriptive statistics. The important thing here is they centered the variables, taking the mean, subtracting the mean from each of the values, and then they did all the analysis, the mean, the standard deviation, minimum, maximum, after they subtracted the mean from each individual value. They did a correlation matrix, and we saw that there were several issues of possible collinearity, or I would definitely say that there were collinearity issues. I told you I didn't like this where they multiply the correlation coefficient by 100, because then the max becomes 100, but that's not the correlation coefficient. The correlation coefficient is between -1 and +1, so for values. And we circled these 4 possible collinearity issues. Sex and height with height. We had age squared with age cubed. We had sex and height cubed with a height squared. We had sex by age with sex by age cubed. So those 4, you wouldn't want to put any 2 of those together. Okay. We were doing the backwards elimination, and we were trying to use CP method. And so we wanted the smallest CP, and that means that that's closest to p plus 1. Okay. And so we looked at these two that were not very close, and I would say that the CP method is a very difficult method to use. Okay. Now, we said that CP of 14 is the maximum model, and it's equal to C plus or P plus 1. And so when we looked at this, we saw that, let's see, we need 1. So let's see, 10, 12. 12 is pretty close to P plus 1, which is 13. 10 is a little far away from 12, which is P plus 1. That'd be 8 and 11. That's 3 difference. 10 and 6, that'd be 4. 9 and 4, that'd be 5. 8 and 2, that's pretty large. 6 and a little over 1. I'm sorry, 7 and a little over 1, that's too big. So 1.15 would give you a, and 5, that's a little far away. Let's see, and so then we said that 2, that would be 3, and 0.5, that's a little far away. And then all of a sudden we have this large value. So it's very hard to pick the best model using CP. And so we may choose a model with 2 variables, height and age cubed, based on the CP. So height and age cubed, and, oh, I see, here. And so that would be the 2 that were left, right, that's right. So we have to look at, so this is just 1, this is 2, and again, 3 variables moving all the variables up. So what they did here is which variable was removed, I think is what that was. Or actually, yeah, so removed. Okay, so that's what that should say, removed. Okay, and so it was very difficult again. Okay, so we wanted to look at the 2 fixed order, the interaction ordering and the power ordering. We started with the interaction ordering so that we would start with, let's see, and within that we looked at the highest power too. So we have interaction with the highest powers here, and then the lower powers, and then individual highest power, and then next, and then we had interaction with just 1 power each, and then the individual variables. So that was the ordering that we had in this. And what we said was this was the smallest CP. Oops. So we said that this was the smallest CP. This had sex and height in it, and 5 and 3.6. So P plus 1 is 5, and 3.6 is not that far away, 1.4 away. So we said that we might use sex times height, and that's a single interaction term. The problem with that is when you have interaction like this, you should also have the individual variables in it. That's called the hierarchical model requirement. And so we don't like to just use an interaction by itself in a model. Okay. And so again, this is for data set 1, and then we looked at the power ordered. So powers have more of a so we eliminate interaction terms first by power, then by polynomials. So we have power, the cubed and interaction, first. Cubed and interaction, then we have interaction and squares, then we have interactions and ones, and then we have cubes, squares, and then individuals. Okay, so this is ranked by power, but power and interaction in a different order than this previous table up here. Okay, and here we said we might choose the second model since it has, let's see, so we have a 4.83, so that was the model with 5 in it. And then we had, so we had that one, and then we had below it, that was 5 and 6, so we'd probably choose the one with 4.83, is not too far away from 6. And we saw a small decrease from 6.33 to 6.27 for the model with 6 in there. And so we might choose the second model when we look at the R squared value because it's higher than the previous one. Or let's see, previous was 6. Yeah, I'm not. Oh, in the previous selection, this way, where we had 0.624 for the R squared. Okay, so we stop there, and now we come back and we say, now let's look at data set 2. We've chosen the model. For the chosen model, we're going to compute the predicted value for the ith observation using the model with sex. Let's see. So we have sex, we have height, and then we have age, and we have height squared, and then we have age squared. And what we're doing is we're subtracting the means because that's what we had done earlier. So we're having a centered model. So we use these, we're using this equation to do our predicted value. Now, I want to note that I will not ask you to do this centered model. Okay, so we will not use a model that's centered like this. If you're going to center it, you might as well standardize it. So you might as well perform z transformations of all the values so that you have a mean of 0 and a variance of 1. All right. If you're going to do that, then it makes comparing them easier because they're all standardized. But if you're just subtracting the mean, then the only thing that you're doing is you are centering everything at 0, and that may help you mentally understand the model better, but it doesn't it doesn't take into account the variation, so you still have different variances for each of the variables, and I find that confusing. Okay, so a difference away from the mean of 0 means a different thing and is interpreted differently when the variance or standard deviation is a different number. So I don't really prefer this centering method when it comes to actual application. When it comes to calculations and derivations, absolutely I prefer this method because then the means and expected values go to 0 for everything. Okay, so we can compute R squared for the second model. We get 621, and R squared for the first data set, and we get 0.627. So the shrinkage on the cross-validation is R1 squared minus R2 squared, and that's a difference of 0.006, which is less than our cutoff of 0.1, so this model is considered reliable. Okay? The difference in the R squared values between the two data sets that we divided this into. So again, we divided the data set, let me find it, into randomly divided this into data set 1, which we've performed all of the selection of the model on up to this point. And then we compare the R squared of both of these to determine the reliability. And that's what we've done in this last step. Okay, so let's move on to our last problem, which is problem 1. And we want to add the variables height squared, age by height to the data with weight, height, age, and age squared that was given in the earlier section. So we're going to use the computer program, and we're going to determine the best regression model relating to weight and according to these 5 independent variables. So the first instruction is use the forward selection approach. Okay. So again, this was performed in SAS, and we'll be using R, and I'll do another video that will walk us through how to do the forward and backwards, and hopefully even allow us to determine or use different selection criteria than just the p-value. But we'll see what the packages that are available do. Okay, so we have this so R squared selection method, and I'm going to come down here and get rid of some of these notes. So that needs to come back, and I can do this, and then I previously forgot that we want to use the smallest CP, And so I was circling the wrong model. Okay, so let's see what we've got. For the for the lowest CP, it would be a negative here, and that would be age times height. All right. If we're using r squared, this is not the adjusted r squared. Then we see that the highest, again, I've circled the wrong one, I didn't notice the first one, is there. So it's age times height. Again, this violates our hierarchical, easy for me to say, hierarchical model convention. And that is that if you have the interaction, you need to have the main effects, age and height, separately. If I look at age and height, and then with age, so here is age, height, so with this model, so if I say that because I chose age times height, then I will leave that model and I will add height and add age to it, because age times height, then what happens is I get a 0.7802, which is better than that one as far as the r squared, but that's going to increase because we've added more variables. And then I look at the CP, which is much higher though, okay? And so here the CP should be small and close to 2. So we might choose this, we might choose this. Since this has a higher r squared value, I chose it, okay? So, and we look at this model with height and age, and we see that p plus 1 would be 4, and we've got a CP of 2.7. That's fairly close. That's less than 1.3 away. So we'd say that's a pretty good one. And then we see that r squared is a little bit higher than it was for the single variable here. Okay, so get rid of this. Now we look at two variables, and the highest r squared is 0.7800, and the smallest CP is 0.7, and so that's a little ways away from 3. And so if we wanted, so based on using the CP and a p plus 1 of 3, we would probably choose one of these three models here, and they're all very close, and the r squared value is all very close again here, okay? If we were just using the r squared, then we would choose the 7800, the first one, which is age and height, and which does not violate any hierarchical model convention. Okay. Now, if we're looking at three variables, we see that the highest r squared is here, and it has height, height squared, and age times height. Again, this violates our hierarchical model assumption. We would want to add age to this in order to have the main effect for this interaction. Okay, and when we look at CP, again, we want to be close to 4, and I think that this one is pretty close to 4. Let's see, so this is close, small and closer, so it looks like this would be the one that's closest to 4 and small, okay? Or actually, we want the smallest that's closest to 4, so very difficult to choose here which one of these we would choose. Might be this one, because again, 1.3, a little over 1.3 is the difference. If we want as close to 4 as possible, it would be this one with height, age, height squared, and age, height. Okay. So again, very difficult to choose a model using CP. R squared is, again, I would prefer to use the adjusted R squared, but again, there's not a scientific method for that, so we use the R squared. But remember that adding a variable increases the R squared. What we have to do is we have to be careful what we're comparing. You say, well, let's see, 7, 5. So these two are actually smaller than this with just 1. What happened? Well, that 1 is an interaction, age and height, and neither one of these models have age times height in it. So we're really not comparing apples to apples. We'd have to, if we want to compare to this first model with age times height, that interaction, then we'd only look at those models that have age height in them. And so when I look at this one, I see that it is higher than 0.75 something. So is this one. So is this one. And so is this one. So we have increased r squared. If we start with this variable and add something else, then we've increased the value of r squared no matter what. If you start with something different and add a variable, that's different. That's a different comparison. So be very careful when you're comparing the r squared and analyzing this. It was something I noticed when I said, well, wait a minute, why are the r squareds up here lower than they are for a 1? And that's because we're not comparing apples to apples. Okay. So the other consideration, remember, is you want the simplest model. You want the simplest models, so the most parsimony, so the simplest model with the best result, the most powerful prediction. Okay. So I'm not going to go through in detail the 4 and 5 variable, but you can see how CP skyrockets up to 6, and that is equal to P plus 1, the maximum model. Okay. And then these are all, we using r squared, we'd want this model, and it looks like it might be the best because this is the smallest CP, and it's pretty close to 5, 4 plus 1, okay, if we were using 4 variables. But again, that's not a very parsimonious model. Okay, so let's see what the book has to say at some point. So again, very, very tedious doing it this way. So, and this is not the forward selection. This is really not a good forward selection. It's not done automatically for us. It's giving every possibility of the forward selections. Okay, models. And it's not in order. Okay, so now let's look at the forward selection model. And so what's going to happen is we're going to look at the p-value for height, age, height squared, age squared, height cubed, age cubed. And then we're going to look at age, height. We're going to look at, let's see, age, height squared, age, height cubed. Oops. We're going to look at height. Oh yeah, and I need age squared. Let's make sure that I specified my maximum model up here. Did I look at it? 5 independent variables. Okay, so the 5 independent variables shown. All right, so these are the 5 independent variables here. So I'm sorry. This is the maximum model. Height, age squared, and age height. Okay, so we're going to look at the p-values for each one of these by itself in a model, and we're going to choose the lowest p-value. And what was done, so I went overboard here with all the possibilities, too big of a maximum model. And so they chose age height because it has the smallest p-value by itself. Okay? And this p-value is less than 0.15. They use a cutoff of 0.15. Here's the r squared, 0.7535, and the CP negative 0.4453. Let's look up here and see which one that was. This is the very first one that I said we'd probably choose, age times height. Again, it violates the hierarchical model. Both, and notice that the intercept is also significant here. Now, no other variable, once we had age times height in the model, no other variable had a p-value, a partial p-value, a partial f-test p-value of less than 0.15. So remember, we just did in our project, we're working on the partial f-test, And so here, this would be the partial f-test of anything given that age times height is already in the model. Okay, so we'd want the f of, we'd check every single one of the other four variables and calculate the p-value with the f statistic, and none of those p-values were less than 0.15, so we stopped. So this is the final model that's given. Weight is equal to beta naught plus beta 5 age times height. And again, this is difficult to interpret, and it doesn't match our convention. So again, we would want to add, that's supposed to be add, not odd, age and height, so we can easily interpret, okay? So that would be what we would do in actual practice. Now we want to use the backward approach. So with the backward approach, all variables are entered into the model, and we look and we see that the r squared is 0.8043, CP is equal to 6 because that's p plus 1, p is 5, and we see the 5, and we see that this is significant at 0.15. However, none of these are significant. When we look at the individual parameters, the p-value of this, none of them are significant. This is type 2 sums of squares, so this is looking at the significance in the full model. Okay. Now, we do see the worst one is here. And since this is the least significant, the highest p-value, it's going to be removed first. We're going to remove age squared. So let's remove age squared. Our r squared value stays the same, but our CP goes from 6 to 4. Our overall model is still less than 0.15. Now let's look, but still none of our individual variables are significant in here, including the intercept. Okay, so the one that's least significant with the highest p-value is age. So we're going to remove age. That's what the computer will do. This is an automatic backward selection method, or backward elimination. So age is removed. Our r squared drops a little bit. Our CP drops a little bit. Now we have 3 variables, so 4 would be p plus 1, right? So if we remove 2 variables, so we have 3 left. So height squared, and age height. And it turns out that the largest p-value that's not the intercept, we do not remove the intercept until we get to the end, then we determine if we need to, is going to be for height squared. So we remove it next. So height squared is removed. Our r squared drops a little bit more. Again, we've removed something from the model, so r squared is going to go down. Our CP has decreased. Let's see, it was what up here? It was a 2.04, and p plus 1 is now down to 3, and this is a little ways away from that, but not, it's a little over 2 below that, but small, so maybe acceptable if we're using that, but we're really not right now. We're looking at p-values. Again, the overall model is highly significant, but none of the coefficients are. So the intercept, height, and age times height are not significant at, actually, yes, sorry, I take that back. Age times height is significant, okay? Age times height is significant at 0.15, less than 0.15, which is our cutoff that we're using. So the least significant is going to be height. We remove that. So height is removed. R squared drops a little bit more. Our CP goes negative, 0.4453. Remember that p plus 1 is a 2. So this is about 1.6 below, or 1.4 something below that. We're highly significant for the model. When we look at, and remember this, and now that we're to a straight line or to a single variable, the overall f-test and the f-test or t-test for the coefficient are going to be the same. And now look what happens to our intercept. It's now significant. So we're going to end up with the same model. So all variables left in the model are significant at the 0.15 level. And so here is the summary that you are given for the backwards elimination. It tells you the step and which variable was removed and the number of variables in the model. It gives you the partial R square, and it gives you the model R squared, which we've been looking at, the CP, and the overall p-value. And so, interesting, the f value was rounded to 0 there, so highly significant, just to 2 decimal places. So it was not 0 at the 3rd or 4th decimal place. And we see that this decreases, these are the p-values of the variables that were removed. And so again, we're left with the same model that we had for forward selection, which is beta naught hat plus beta 5 hat age times height. So again, it does not meet our hierarchy model or hierarchical model convention. Now, part C, we're going to use an approach that first determines the best model employing height and age as the only candidate independent variables. And then we're going to determine whether any second order terms should be added to the model. We're going to now, instead of using alpha equals 0.15, we're going to use 0.1. So the first thing that we do is we look at the model with both of these in here. I have to admit that I do not like this method. Again, I would look at height and age, and then I would look at, so I would choose the best one of those, and then I would see if height, if age, let's say it was height, and if I chose height, and I think that's what gets chosen here, yes, the most significant here is height. So we would choose height in the first step of our model, and let's see, these are type 1. Okay, so yes, so type 1, so height would be the first one, and so we would include height in the model. And then the type 1, we would check for age, and it looks like age is significant at alpha equals 0.1, so we would end up with height and age, and then and only then would I look at the second order. If age was not included, I would stop, and I would not look at the interaction terms, okay? Not really. Now, I could look at it and say, okay, height and age, height times age and height. If that's a very good model, then I would say, okay, now let's look at, let's say that first would be this, and let's say the next thing would be height times age would be the best choice. Then what I would do is I would add age and look at height, age, and age times height. And I would compare those models and see which one I thought was the best, okay? But that's not what we're doing here. We're looking at height and age first. And so, so both height and age are significant, so both are added to the model, and we're going to look at second order terms. Now, again, the way this does it is, this is type 1 SS, but this is doing it in a particular order. If this is not the best order, then this is really bad analysis. But in any case, none of these are significant at the type 1, and none are significant at the type 3. So notice that by adding these other variables, age is just barely non-significant now, or not significant at alpha equals 0.1. So this would cast doubt on age, but we've already looked at age and height together, and both are significant. So we know that that's an okay model. The type 3 does the variables added last. None of these are significant, but that's with 5 variables in the model. So this selection method here is not what I would do, and not what the person who taught me this course would do either. Both of us agree that what we would do, first, it's not a simple method to in this method, there's not a simple way to select the best model because of the data that we have available. We only have the type 1 SS in that order and the type 3 SS, which is not, this is not what we would use. What we should do is look at the 3 separate models. So the first would be, since age and height are in there, I would keep age and height in all of them, and then I would look at the other possible variables one at a time. I would have age times height and that p-value, and then I'd have age squared and look at that p-value, and then I'd look at age, height, and height squared and look at that p-value, and if any of these p-values were less than 0.1, I would use that model. Okay, that was done, and it did not change. None of these were selected. So this was done. None of the p-values were less than 0.1. So our final model is beta naught hat plus beta 1 hat height plus beta 2 hat age. I want to point out that when you're doing analysis, you need to be consistent with what beta 1 is and what beta 2 is. So once you assign beta 1 to height, it stays with it no matter what other analysis you do with that problem. And the same thing with age. Beta 2 stays with age. Be consistent through all of your analysis. Do not change the subscripts. Don't reverse these, or just because you don't have them in the model doesn't mean that it doesn't stay the same. So once you set out a convention for which number in the subscript here, let me zoom in here, if we're going to call beta 1 the coefficient for height, it's always the coefficient for height in that problem, okay? So always designate it the same number and keep it consistent so that you don't confuse your reader, okay? So that is the best practice there. All right, so part D, compare and discuss the models obtained for each of the approaches above. So the models in A and B, remember this was forward, and this was backward. And they both came up with the same model, which was weight equals beta naught plus beta 5 age height. Okay. So even though beta 1, beta 2, beta 3, and beta 4 are not in the model, we assign beta 5 as the coefficient for age times height, so we keep that. So both of these resulted in the same model. It's generally not true that backwards and forwards give you the same result, but it does happen quite frequently. It's just not always true. Okay, and they only include the interaction between age and height, which is what I've written up here. I've written the model. And note that models in which interactions are included, but the main effects from the interaction are said to violate the principle of the model hierarchy. That's easier to say than hierarchical. Okay, for me anyway. And these models can be difficult to interpret, and that's the key. Okay. In Model C, that's where we looked at age and height before we looked at the others. It does not violate the principle of model hierarchy. And it has a somewhat higher R squared and a fairly similar MSE compared to the model in A and B. So let's look at that real quick. So the MSE is 28.9. And so, is that right? Or is it this one? I'm sorry. That has all the things in it. So it's 21.7. That's the, this has age and height in there only. This model down here has 5 in there. So that's not the model. That's the full model with 5, okay? Or the maximum model. So let's see if we've got the MSE. So let's go up and look at the, I think maybe that table has MSE, yes. So if we look at this table and we find just age height. The MSE here is 21.89. R squared is 0.75. And if we look at this height times age, or height and age separately here, we see that the R squared is 0.78, so it's higher, and MSE is only slightly lower. So it's much better for us to choose height and age instead of the interaction term, and it's much easier for us to interpret. All right, I know this has been a long video, and I apologize for it, but I don't like what I did last time, which was cutting off in almost the end of an example. So I think it's better for us to finish and have continuity in one video. All right, so that's it for this chapter and this video. Please don't forget to scan your lecture notes by midnight of the date listed in the course calendar. If you have questions, come to virtual office hours. If you can't come to virtual office hours before you need an answer, please email me. But I need your work, a picture of your work or your work. If it's an RMD file, send me your RMD file, your work or a picture of it, and the problem, so that I know both of these and can help you. All right, please take care of yourself, stay safe, and we hope to see you next time.